future, this course and along with the part A will all be available in self-paced format on NanoHub. Guess it's now time for a little epilogue. Now, in part B, as you know, this is about quantum transport, and you might, as you might expect, quantum transport kind of starts with the Schrodinger equation for quantum mechanics, this E psi equals H psi, where H is this matrix whose eigenvalues tell you these energy levels available for conduction. But as we discussed in part A, just having the mechanics is not enough to describe transport, because transport involves mechanics as well as these entropy-driven thermodynamic processes. And in the context of semi-classical transport, which we discussed in part A, you have to combine the Newton's laws, the mechanics, semi-classical mechanics, with the entropy-driven processes, which is this right-hand side of the Boltzmann equation. And this is the Boltzmann equation, which is the centerpiece of all semi-classical transport. Now, in quantum transport, I guess we replace this mechanics part with Schrodinger equation, that's quantum mechanics, but then you have to add the entropy-driven part. And this, in this NEGF method, enters through the self-energy functions. So we have this sigma 1, sigma 2 describing your two contacts, and the sigma 0 describing the interactions of the electron with the surroundings in the channel. And this leads to these additional terms in the Schrodinger equation. I guess it's a modified Schrodinger equation. And H has to be Hermitian in order to conserve probability, but this sigma is actually non-Hermitian, which means because of this sigma, if you start out the system in with certain number of electrons, these electrons will actually want to leak out of the system. Probability won't be conserved. So this will lead to outflow. But then there's also this inflow term, because new electrons come in from the contacts. So the idea is you have electrons here which go out into the contacts and new ones come in. And that's described by these additional terms. So how does this relate to the NEGF equations, which, as I say, is like the centerpiece in this quantum transport? Well, what I'll show in the next slide is how you can get from this, what you call a one-electron Schrodinger equation, to the NEGF equations. And there's also this current operator, which you need to calculate current, but I won't be talking about this since we have talked about it in the actual course, but this is just an epilogue to kind of give you an overview and sum things up. Now, so I'll focus on this. And the main point I wanted to make here is also that this is really the same as the standard NEGF equations that are usually derived using much more advanced techniques, following the original work from the 1960s. The seminal work of Kadanoff and Bain and Keldysh and others. And the main thing I've changed here is this notation. That is, the standard literature uses G less and sigma less, whereas we multiply by minus I and call it Gn and sigma n. Because the Gn is, the physical significance is it's like electron density. The sigma n is like inflow. So how do you get from this equation to the NEGF equations? Well, the point is that if you start from this modified Schrodinger equation, you could write the psi in terms of the source term and what goes in between. So this is obtained by a straightforward matrix inversion from here. And what you get here, that's what you call the retarded Green's function. But this gives you psi in terms of S, but it's inconvenient to work directly with this Schrodinger equation because when you have multiple sources, like S1 and S2, if you work like this and put in S1 plus S2, you'll get interference between them, which is not physical because these are incoherent sources. There are no interference terms experimentally. And it's more convenient then to actually work with the psi star, the psi dagger, which is what we call Gn, and SS dagger, which is sigma n. So in that sense, this is like I guess psi star is interpreted as probability for individual electrons, but then when you have hundreds of electrons, you could interpret it as the electron density. And similarly, the source term, its strength is what we call sigma n. And where do we get this? Well, just from here. See, psi equals GRS. So psi dagger is GRS, and then GRF, dagger of the whole thing, which is S dagger, GA. GA being the conjugate transpose of GR. So that then gets us this NEGF equation. And as you can see, it's a one-line derivation literally. Okay? And this is what I've been doing in my books usually for many years now. But the standard derivation of this equation, though, uses much more advanced techniques following the original work back in the 60s, as I mentioned. So the Keldysh paper, the title of the paper was Diagram Technique for Non-Equilibrium Processes. And what was considered there was, I guess, this dissipative processes that involve energy dissipation from the electrons into the surroundings. And to describe such processes, because it involves how energy from electron goes into many degrees of freedom, you need this many-body theory. And so what is used here is what's called this many-body perturbation theory. Now, why wasn't this simple derivation done? Well, that's because of this mindset in general, that transport essentially involves many-body processes, and you cannot talk about current flow without many-body processes. That was the general mindset. So before 1990, that is before the advent of mesoscopic physics, the view was that the essential physics of current and flow and resistance is in dissipative processes. And the contacts and the elastic interactions, that's kind of an unimportant detail. Now, what mesoscopic physics taught us is that contacts are important. And so before 1990, theoretical papers often didn't even draw the contacts. But these days, usually people do. And so the feeling is, of course, essential physics is still dissipation, but then contacts are an additional detail. Whereas the perspective I have tried to convey is that the essential physics of resistance you can understand in terms of the contacts and elastic interactions. And the dissipation is kind of an additional detail. And this is very different from what you normally hear. And so let me elaborate on that a little more. So why is it that people think dissipation and many-body processes are kind of integral to this idea of current flow? Well, that's because of something you may have heard in undergraduate, that if when you turn on your switch and a light bulb goes on, if one electron actually had to go from here to there, you would be waiting a long time for the light to turn on. But in practice, the light turns on immediately, and that's because one electron doesn't go from here to there. What it does is it pushes the next electron, and that one pushes the next one, and that's how the signal travels. And so there's this feeling that current flow, or this conduction process, is inherently a many-body process. It's not about one electron going through, but rather one thing pushing another and so on. But the point I want to make is that this process is actually modeled quite well in terms of a distributed RLC transmission line, where you have these series resistors and inductors and these capacitors in parallel. And usually this inductance has a magnetostatic component, the part that comes from magnetostatics, and a kinetic component, the part that comes from transport theory of the type we are talking about. Similarly, the capacitance has an electrostatic part and this quantum capacitance, the part that's related to transport or density of states type of properties. And if you look at the velocity, which is usually 1 over square root of LC, if we use the magnetostatic L and the electrostatic C, you'll get the velocity of electromagnetic waves. Whereas if you look at the transport ones, then it will give you the velocity of electrons. And usually, what happens is the inductance is dominated by Ln and the C is dominated by Ce, and so the signal travels at the velocity of light. In very small conductors, that could reverse, and you could have situations where signals travel much slower. But usually, this is what you would have. But the point I'm trying to make is, all that is captured very well in this magnetostatic capacitance and electrostatic capacitance, and doesn't need to be part of how we calculate the resistance. The resistance that goes in there, that really doesn't involve any many-body theory. You can understand it at least to first order, and you can understand it in relatively simple terms. Now, let me explain this point a little. This is something that has become clearer, I guess, with the advent of mesoscopic physics and nanoelectronics. Because one of the things mesoscopic physics taught us is that a ballistic conductor has a resistance, this Rb, which can be associated with the two interfaces. And if in the middle of your channel you happen to have a scatterer, like a little hole in there, then the transmission of electrons from left to right is something less than 1, this T, and so the resistance is higher. It's the ballistic resistance divided by T. And this additional resistance is what you can associate with the channel. So this is well established, this is understood, you call it Landauer formula. But the part that causes confusion still is, how do we take this and divide it up into a part that's associated with the interface and a part that's associated with the channel? Because the common wisdom is that, of course, if you want to locate where the resistance is, you should follow the heat, because resistance gives rise to heating, and so wherever there's a resistance, there must be heat. But this is not correct, because, you see, if we had a hole in the middle of the channel, it's obvious that the hole is what's causing the resistance. That's common sense. On the other hand, the heat that is associated with that resistance is also obviously not being dissipated in the hole, because, you see, a hole cannot dissipate heat. Heat meaning that the energy from the electrons has to go out into the lattice, start the atoms vibrating and jiggling around, and that's what heat is. And a hole just doesn't have the degrees of freedom to dissipate your heat. So intuitively you can see that this hole causes the resistance, but can't really dissipate the heat. So it makes sense to associate that resistance with the hole right there. But then, if you associate the resistance with heat, it's completely wrong, because that heat is actually distributed all over the place. Okay? So how could you come up with a quantitative criterion that would allow you to locate where that resistance is? And in part A, what we argued is, what you have to do is follow the voltage. This is a series circuit. The current is the same everywhere. So wherever there's a resistance, there's a voltage drop. But this leads to the question, what is the voltage? Which voltage do you look at? And the answer is what we know, what device physicists know very well, and well established in solid state physics, that what is important is the electrochemical potential and not the electrostatic potential. So on a macroscopic scale, that's usually well known. It's just that when it comes to small conductors, people are usually nervous about talking about the electrochemical potential. And that is where, what we argued in part A, I think this was unit 3, that if you looked at how the electrochemical potential changes, you'd see a profile like this. And indeed, there would be a drop here that corresponds to this interface resistance, another one corresponding to that interface resistance, and a drop here that corresponds to this channel resistance. But to understand this, you have to invoke this concept of quasi-Fermi levels. The idea that in a small conductor, the right-moving carriers can have a different electrochemical potential or quasi-Fermi level compared to the left-moving electrons. So if you look at the right-moving electrons, it has this profile, this profile, and the average is what this black represents. Now, why does this profile drop suddenly at this scattering? Look at that drop. Well, that looks like a major voltage drop. And so there must be a power dissipated that's V times I. And the answer is no. this quasi-Fermi level should not be viewed as an average energy of the carrier, only the degree of filling of states. So the fact that it drops suddenly means that if you looked at the right moving states, all be filled at this end, but as you cross the scatterer, they suddenly become relatively empty. That's all. Why is that? Well, that's because of some know from common experience. If you're going down a highway and there's a road somewhere, like a construction zone, then before the construction zone, you have a traffic jam. You cross the construction zone, the road's all empty. That's basically what it's saying. You have this electronic with a little construction zone here, this bottleneck. The states are all filled up right here, big traffic jam. Right here, all the states are relatively empty. That's it. See? But the point to note is this quasi-Fermi level should not be associated with the average energy of the carriers. Because whenever you have a roadblock like this, if you look carefully at the electron energy distribution, you'll find that it is way out of equilibrium, which means the electrons are hot. So what this hole does is it causes the electrons to get hot. And the electrons eventually, of course, get rid of the heat to the surroundings. But where that happens depends on the details of the problem. It could easily happen 1 micron away from here. Okay? So this was this concept that we talked about in part A. And the question is, could you capture this in a quantum treatment? This little semi-classical picture, because the plots I drew, this semi-classical picture, that's what you get out of Boltzmann equation. Now in NEGF, what we discussed, I guess in this part, I think this was unit 2, we went through this example, that if we do a coherent treatment, which means if you only take into account the 2 contacts and ignore any interactions inside, then you'll get this black curve. So the red is the semi-classical, what you get out of Boltzmann. The black is the coherent NEGF treatment. That's what you get. Now, in practice, you wouldn't usually see all these oscillations. Why? Because in a real solid, there's all these random potentials. As the electron is going through, there's all these atoms jiggling around, which the electron feels in the form of this random scattering potential, and which destroys this phase. And NEGF allows you to put that into the model through the sigma 0. And if you put that in, the sigma 0, when you include that, then you'll get a plot that looks like this. If you include sigma 0 such that there's only phase relaxation, then as you can see, these oscillations have died out. The black looks almost like the red, but with some remnant fluctuations around it. Now, if you include interactions that also relax momentum and not just phase, then you'll get a plot looking like this, where the oscillations have died out, but in addition there's a slope here. Why? Because the momentum relaxation gives you a distributed resistance. Because of the distributed resistance, there's a slope in the voltage. And all this physics can be included by choosing this D carefully. So these interaction sigmas are related to the G's through this D, which has a simple physical meaning. This is actually a tensor, but what it represents is the mean square value of the scattering potential. So it has the dimensions of energy squared. It's like if this is 1 electron volt, that would be like 1 electron volt squared. And by choosing the structure of this tensor carefully, you can get phase relaxation, or you can get momentum and phase relaxation, or one thing we are working on these days is spin relaxation. So you could incorporate all that into the model. But the point is, none of this includes any dissipative processes inside the channel. In other words, what you're really assuming is all the dissipation occurs in the contacts. Usually makes this calculation relatively simple. And the point I'm trying to make is, even though dissipation is not included explicitly, the physics of resistance is all coming in very nicely. A barrier, this barrier which represents the hole, does give you a drop in the voltage, giving you a resistance as you'd expect. All that physics is in accord with intuition. So would dissipative processes make a difference? The answer is it could, depending on the problem at hand. So the way I think is, at a given energy, you could think of it as these resistors in series. There's the interface resistance and there's the channel resistance, and you can draw a view like so. But then there are many, many energy channels. So each energy channel you could view like this. Now, if you looked at the mu, usually at each energy, if you looked at how the mu varies, in principle it could be different for the different energies. Which means, in the most general case, you should think of it as if the mu has an energy dependence. If you're trying to, this mu represents this filling of the states, but the point is that itself could be different for different energies, and you might need a different mu to represent it. Now, the point, what inelastic processes do is, they give you couplings between different energy levels. And so, they cause what you might call vertical flow. They cause current flow from one energy channel into the other. But then, if you have uniform contacts, and if all the energy channels conduct relatively equally, then what you might expect is that the potential at these points and different energy channels are almost the same. And in that case, adding an inelastic process will not change the overall resistance that you calculate, because there will be hardly any vertical flow. And that's why usually for low bias in uniform materials, if you ignore the dissipation, that is, if you ignore these connections and just say all dissipation occurs in the contact, the resistance you calculate is right, is correct. It matches what you get from the rigorous theory. But this doesn't necessarily have to be the case. For example, even this problem that we talked about with the barrier in between, if you look carefully, you see these energies don't conduct as well as those energies because of the barrier. And so, what electrons will tend to do, if you include inelastic processes into the model, is they will rise up in energy, try to travel here and then come back, which means on this side, it could actually absorb heat from the lattice. So thereby cooling the solid. So this side could get cooled while this side gets heated. Right? And this would be kind of like the Peltier effect. This is a thermoelectric effect. And these are things that would come out of a detailed NEGF model, provided you include the inelastic processes. And of course, if you don't include the inelastic processes, you'll miss all that. And overall resistance you calculate would also be a little bit off, because you wouldn't have the vertical flow in your model. Now, you may have non-uniform contacts. In other words, so far we have talked about uniform contact, but supposing you have non-uniform contacts, where on this side you connect to this energy level, but on this side you connect to many energy levels. So this is kind of what you have in a transistor when you at high bias, because on the drain side you've applied a positive potential and lowered the conduction band edge. Well, then again, you might expect a lot of vertical flow, which could affect the overall current and the resistance. A more striking example is one where one contact connects here and one contact connects there. Like in a p-n junction, where you could have one contact that connects to the conduction band, another one that connects to the valence band. And then if you don't have vertical flow, you don't have any current flow at all. And only current that you actually get is because of the vertical flow. These what you, in a p-n junction, what you would have called recombination generation processes. So the bottom line is that there are many cases which you have talked about where you can calculate resistance correctly without including this vertical flow. But that's not necessarily true. Right? There are many problems that do require it. But the main point I'm really trying to make is that in general, there is that mindset that current flow and resistance requires many body processes. And so, in order to get started, in order to understand where these equations come from, you first have to master many-body theory. And so NEGF is viewed as this esoteric tool, which is only accessible after you have mastered many-body theory. And I've quoted from the preface of a recent book, an excellent book, by the way, but which kind of says what the common perception is about NEGF. And the point I have tried to make is, well, if you just consider elastic interactions, then you can use relatively straightforward one-electron theory to get the same equations. And even the dissipative processes, if you stick to the lowest approximation, that's the Born approximation, then you can get the correct answers out of one-electron theory, but you have to be careful about these exclusion principle factors. And so you could get started with one-electron theory, learn these equations, learn how to use them, and then, as needed for different problems, figure out how to get the required sigma. And in this sense, you can think of the Boltzmann equation. As I say, Boltzmann equation has these scattering terms on the right. How do you calculate the scattering terms? Well, the methods have evolved. You often use this Fermi's golden rule, which came long after Boltzmann. And similarly here, we'd expect that as we go along, as we look at different problems, we'll come up with new better ways of calculating these sigmas or this self-consistent potential U that you need. New methods will come up, and some of these might actually need non-perturbative methods for strong interactions, for example. But those can evolve as we go along. But in order to get started, it's not like you need to learn many-body theory right away. And this part of the problem, where you're neglecting inelastic processes completely, that itself is relevant to many current problems in nanoelectronics. And let me just give you one example before I wind up. And that is this problem that we talked about in Unit 4 of this course. One of the major developments in the last few decades has been these magnetic contacts, which can inject spins preferentially. And for this discussion, let's assume we have a perfect red magnet which only injects and detects up spins, the red spins, and a blue magnet which can only inject or detect down spins. And so if 100 electrons come in here per second, they will flood this channel. None of them can go out here, so there's no current here. All of them will go out there, all 100 of them. And out here, you won't get any. So this would be the situation with these four magnets. The question is, what happens if this magnet, instead of being pointing down, is actually pointing sideways? Then the answer is, of these 100 electrons that come in per second, 50 of them go out here, half of them. Why? Well, because an upspin is a superposition of a left and a right. And this is very non-intuitive, of course. What you are probably more familiar with is for photons, where you think of polarization as a vector, then you're used to decomposing a vector like this into two components, 45 degrees on either side. Whereas here, it's like 90 degrees on either side, and it requires a whole different algebra, the spin-offs. Okay? But the whole superposition principle is, of course, at the heart of all the mysteries of quantum mechanics that have bothered so many people. The idea that one electron, even though we know everything about it, we know it's an upspin electron, and yet we cannot predict whether it will go out there or not. It only has a 50% probability of going out. Of course, if you do the experiment with hundreds of electrons, then you can say that half of them will go out, which is what we are doing, steady state experiments, lots of electrons. Well, what happens on this side of the 50? Again, you can view the 50 here, which are pointing to the left here. Those are again superpositions of down and up. And so half of them, 25, will go out at this up magnet, and the other 25 will go down the channel and come out at the down magnet. So overall, you see what happened was, I turned this magnet, instead of being pointing down, I pointed it sideways. And I have no current here, and now I have lots of current there. And in principle, you could work out how this number would change as you change the direction of this magnet from up as you rotate it down, and you'd get a curve looking something like this. That if it is either up or down, you don't get much current, but you get lots of current once it's sideways. Okay? And this is the basis for, I guess, close to some of the ideas for spin transistors that you see in the literature. And of course, whether this is useful as a device, that remains to be seen. But right now, I'm just trying to make the point that there's all kinds of things involving subtle quantum mechanics, which are now technologically accessible with solid-state devices. And all of this you could model using this NEGF theory that we discussed. Where you have an H that describes your channel, the sigmas that describe these contacts, and if you want to include spin scattering, you could do that also with the sigma 0. And one of the interesting things people are looking at in this context of spin transport is this idea of spin circuits. Because one of the major challenges with NEGF is that although in principle you can handle any device, but the fact that you're keeping track of all these off-diagonal elements makes it gradually, I guess, big devices become numerically intractable. Whereas in a semi-classical treatment, you only keep the diagonal elements. So if there are n diagonal elements, there's kind of like n squared off-diagonal elements. Now, but all those off-diagonal
The one will also instantaneously change, right? So have people actually been able to do something like that in the lab?
So that's what I think you hear of new experiments in the last 5-10 years, right? A lot of these, many with photons. I guess what you're wondering is whether anything has been done with electrons. Right? With photons, you hear that all the time. Do you know if there's with electrons?
There is some electron, this Cooper pair splitting in this Columbia group is doing. So what is they do in indium arsenide quantum wire? They inject a Cooper pair with one electron. Cooper pair means two electron pair with opposite spin. So opposite spin is singlet is like entangled. You can write the function like that. So that they take a Y junction, they split, and they retain the information. And when they again superpose other side of the quantum wire, they retrieve the information. So
It's a recent experiment?
this is a recent experiment, very recent. It is a Hungary group in Hungary and in Colombia, both almost simultaneously.
Oh, it's two separate groups.
What's the name of the experiment?
This is called Cooper pair splitting.
I'm not sure about the details, but in these centers in diagonal,
Pardon?
in these centers in diagonal also show the same things.
Yeah.
There are, I'm not sure.
But are they entangled?
Yes. Yes. Actually, if this, the good thing is they can get this thing. There is interface.
This is like a vacancy.
Yeah,
So what he's saying that there is a group in Australia which
Professor Bhaskar and Murugaran was saying about that. In these centers in Diamond, it has been shown that these two spins were put 3 meters apart and still they showed entangled states experimentally. I'm not sure about the whole details, but he wrote it.
Yeah, because one thing is that the classical version of it is relatively clear, which is what you call correlations. Right? It's being this superposition that is not so, that's tricky and involves some very delicate phase-related issues. Even what I was talking about the other day with the p-bits, the thing is, you have two magnets and you could be this, or this. and you could arrange it so you are here. So 50-50. So it's either one magnet is up, other magnet is down, one magnet down, other magnet is up. But the difference with qubits is qubits kind of would be in both together. It would be a superposition with a certain phase relationship. Please go ahead. Yeah.
You have a pick up for party. Oh. Yeah, this one, yeah, there is, I guess there is something, but I don't know if you want to watch one more. Yeah, there was something that kind of was transition from part A to part B, which is kind of like that. Yeah, this one emphasized part B more, but brought in the part A.
So, my suggestion is that T30, see there is no question, you can break for T and come back here 4. And then again you can have, if you have some more question, you can discuss and then finally distribute the certificates. Okay? Or if any of